No.
All right. Okay. Hi, everyone. There's a quiz. Okay. Hey, everyone. So there's a quiz. So that's the quiz. There's gonna be quizzes often from now on. Here what we have is the example from before, right? So the idea here is you just count how many times does this guy get computed essentially. And the answer is, well, as many as there are going to be entries in mem eventually, which is about n, right? So going back to what we did there, so basically what it is that you have a tree that looks like this. Right, so here you call n minus 2 1, and this is n minus 1, and this is n minus 2, and this is minus 1. So this is n minus 2. This is, or sorry, it's 1. So this would be n minus 3, minus 2, and minus 3, and minus 4, and so on. And this is going to get called, this is going to get called, this is going to get called, this is going to get called. But then when you call this guy, this already was called. So mem at n at minus 2 is already existing. So it'll just return. So the total number of calls is going to be as many as there are calls over here, plus the ones on the side, which is, you know, another n calls in total. So 2n in total. Does that make sense? So the answer is O. Okay, so this is as opposed to doing things without memorization, where you would be repeatedly computing fib of n minus 2, computing fib n minus 5 a lot of times, and that's why the complexity will be much larger. Yeah.
So it's, we didn't have both of this computer setup, that might for this.
Yeah. Okay. Yeah, and so that was the last lecture from 180, if you remember, where we shown that the exact estimate is actually O of Fibonacci of n, if you want to count all the calls without memorization. All right. Okay, so this is that. So there is a little bit of admin stuff. I think people did pretty well in the exam part of it, is we you know, graded it not extremely harshly, I think pretty fairly though. But there were some people who didn't do so well. So I want to give people the chance to kind of make up for that. So if you do better on the exam, not you, the class, you individually, then the midterm is going to count for 20% as opposed to 30 in the original plan. And the exam is going to count for 55 as opposed to 45. So that's only if the individual does better on the exam. If not, then you get the old one. Okay, so this is just an opportunity. If you do better on the exam, then you'll do better in the course overall. Now, that's not worth very much if the exam is much harder. The exam is not going to be much harder, not in the sense that some of the questions are not going to be hard, but in the sense that if you're asking like, what kind of grade should I expect approximately on the exam? The answer is, well, if you study hard, you'll do better. But on average, I expect that people will do about the same on the exam as on the midterm after whatever adjustment happens on the exam, if there's an adjustment. So if you want to know how you're doing in the course, well, probably a little bit better, hopefully, that on average than what your midterm plus project one mark indicates. Make sense? Okay. So that's that. So I know that today is the drop deadline. If you want to talk to me and get kind of individual advice like today, I am in principle available. Like email me, except for 2 to 3, I think. I'm not booked. Currently, some people asked about advice on catching up, and that really depends on where you are. And maybe so I guess like hopefully if you're here, you don't need to. But I know maybe like it's better to study on YouTube anyways. So if you're really behind, if you feel like you need kind of a systematic reintroduction to C, I recommend the King textbook. So that the King textbook is like by King from the syllabus. So that's basically, like I said in the beginning, a kind of the book that we used in ESC180. So it kind of introduces everything from scratch up to and including linked lists. After that, I think the best you can do is the course notes. So the course notes, we've been working on them for a couple of years. I think they're good now. The pointer exercise is very important. So the pointer questions were not done like amazingly well, I would say, by everyone. So some people did well, but some people did not. I feel like if you internalize the pointer exercises, you should be able to do those. We will also be scheduling kind of weekly catch-up sessions for people who feel like they're behind. So if you answer the poll on Piazza saying when you would want for that to happen, we'll try to make it happen. Okay, that is what I have to say about this. So I want to go back to dynamic programming. And I want to go back, as promised, to the houses example. So that's the houses example. That's the code that you have from before. So you can also copy it from the slides, except for the comments, right? And what I want to do now is I want to get the solution in an elegant way, as opposed to like the inelegant way that we proposed last time. So here's what I'm going to do. I'm going to just copy and paste this. And I want to think about this in terms of what the recursive function currently returns. So currently, it returns the cost of painting houses up to I, where I is painted with color CRL. Okay, so that's just the definition of what this function returns. And the way I'm going to program it is I'm going to first program the doc string. Sometimes it works. And then I'll just fix up the function so that the function corresponds to what's in the doc string. So wouldn't it be convenient if, in addition to the cost, I also return the solution? Yes, so I'll just do that. So far that's just English, right? So that didn't change the function very much. So all we need to do is just fix up the function so that so that it's all consistent. Okay. So base case. If I'm returning houses and at COL at I. So if I is equal to 0, I'm returning houses at COL at I. Why is that? Because if I want to decide what it costs to paint house number 0 COL and everything to the left optimally, that's just the cost of painting the house COL. Sorry, let me stop. Is everyone with me about what the problem is in general with the houses, or should they repeat that? Who wants me to repeat that? Okay. You should have asked before. Okay. So here's how it works. So we have our cost array. And this is, let's say, R, and this is, let's say, G, and this is, let's say, B. And the way the costs work is this is the cost. So 6 is the cost of painting house at index 1 red. And this is the cost of painting the house at index 1 green. And this is the cost of painting the blue. The problem that we want to solve is paint all the houses at minimum cost such that no two adjacent houses have the same color. Okay, so one possible solution, which is probably not optimal, is to say, well, like I'll paint this one red and this one green, and then I'll do this one, blue, and I'll do this one red, and I'll do this one blue, and this one green, and this one red. So no two adjacent houses had the same color because I always was moving in between the lines. So that would be one possible solution. What I want is the minimal cost solution. Okay, does that make sense? Questions? Okay. All right. So now I have my recursive function that I'm writing, where so far I just changed the doc string, where I want to give it houses. So houses would be the cost, and so all the costs. I'm gonna give it the color, and I want to give it I, and I want to return. Given that I'm painting house I with this color, I want to return the total cost of painting everything starting from the extreme left up to house I, with house I being painted COL. That's the job of this function. Make sense? So now I added another thing. So in addition to returning the cost, I also want to return the solution. So first of all, why is this the cost? Can someone tell me why is this correct for the base case? Yeah, someone else. Yeah. So what is the problem that's being posed here? So the problem that's being posed is I know that I want to paint house 0 red. What does it cost to paint house 0 red, as well as everything to the left in the optimal way? Well, there's nothing on the left. So it just costs 7. That only works for house 0, right? But for house 0, I can just say, if I want to paint house 0 red, that's going to cost 7. If I want to paint it green, that's going to cost 3, and so on. That would not work for the next one, because if I want to paint house 1 red, that's cool. That by itself is definitely going to cost 6. But then I need to decide whether I want 6 plus 3 or 6 plus 16. If I want to paint house 2 red, it's definitely going to be the 7, but then it's going to be some kind of sum of 2 of those. I don't know what that you need to figure out. Make sense?
So going back here, this is the base case. So does the base case not make sense to someone now? Okay. All right. So I've added one, sorry, so this is my solution one. So I've added another thing. So in addition to returning just the cost, I also want to return the solution. So I'll return a tuple, two things. So I'm returning the cost and the solution, well, it says in gray, but why is the solution here COL? So what's the problem? The problem is I want to paint the leftmost house red. How much does it cost? And what do I need to paint it? If I want to paint the leftmost house red, what do I need to paint it? Yes, thank you. Okay, so like that's all it's saying, right? Does that make sense now? So okay, questions? Are you with me? Okay. So all right, so we have the base case. So now we have the recursive case. So what do we do recursively? Again, to remind you. So we're saying try every possible color for I minus 1 and get me the color that gives me the lowest cost for everything up to and including house I minus 1. Right? So here I'm asking for color 0, what would it cost? For color 1, what would it cost if I can do it? For color 2, what would it cost if I can do it? If I can't do it because color I is COL, then I just skip. Okay. So, okay. And then I update those guys. So two things that I need to update. So my function is now called cost solution 2. And it returns two things. So it also returns the solution. So that's just kind of to make it correspond, because now we're returning two things. And now, in addition to keeping track of which color right now seems like the best color, I'll also keep track of which solution seems like the best solution. All right. So the magic here is, well, assuming it returns the right thing for I minus 1, I now have both the optimal cost of everything up to house I minus 1, and also the solution that corresponds to that cost. And the solution is just the list of the colors up to I minus 1. Okay. All right. So updated that. Cool. Now here, I'm still returning the cost from last time. I want to return the solution here. What is the solution that corresponds to this cost? Yeah. Not quite, because it's certain Kerman's solution is certainly a part of it, but it's not just Kerman's solution, because Kerman's solution is the solution for 0 up to I minus 1. It's not the solution from 0 up to I. Yeah. No. So you'd think though. So no, because what I'm asking is, what is the close though? That was my first thought too. So what I'm asking is, if I want to paint house I red and also everything to the left, whatever at the minimal cost, what should I paint 0 up to I minus 1. And what should they paint I? What should they paint I? Yes, but in my example, if I want to paint house I red and everything else according to the minimal cost, what should they paint house I? Red, yes, because that was in the condition, right? So I just want to take the solution for 0 up to I minus 1. But then I also want COL. Right? And one way to think about it is I have my cur min. So cur min is the cost up to I minus 1. And then I have this guy, which is the cost for painting house number I. So this is why when I'm computing the cost, I have a sum. And when I'm computing the solution, I stick together the current minimal solution plus the color COL, which I always wanted to paint house I with. Right? And that's just going to be a list, right? So if you remember, this is a list, and then I make this a list, I just stick them together. So I return a list that corresponds to the solution from 0 and up to house I. Yeah.
So, like current min solution plus color there, is that just like a concatenation?
Yeah, exactly.
This is up to the end.
Yes. Make sense? And the way to think about it is just, just recursively. So we just wrote this, and we try to build up the solution that corresponds to the minimal cost. So this, I think, is very easy to believe. So you're just returning the color of the house in the color in which you're painting it. And then here, well, you have the solution from 0 up to I minus 1, and then you have the solution for I, and that's it. That's the solution. Kind of like math, kind of like magic, right? So okay. All right, makes sense. That's it. That is all there is to it. So I want to do the coins a little bit more. You'll do the coins in the lab today as well. So I don't want to give out the entire thing. So to remind you, this is the coins problem, right? So this is from last time. So we have those denominations, D1, D2, and so on. So the example that we had in mind was, what if hypothetically we have, 1 cent, and we have a 4-cent coin, and we have a 5-cent coin, and we have a 10-cent coin? What if we want to make 8? Well, and we want to use the least amount of coins possible? Well, here you can eyeball it and say you need to use 2 coins, 2 coins of 4 cents, right? So that's what we want to get to eventually. Does the problem make sense to everyone? Okay. So what's min cost? So it's the least number of coins needed to make up amount T. Okay. And then the reasoning went like this. So what's min cost T? Well, we're going to use one of the coins. So we're going to either use 1 or 4 or 5 or 10 if it's possible at least one of the coins at least once. Right? So this is the 1. And then we're saying, okay, so if I use denomination D1, then I need this many coins in addition to the D1. And if I use denomination D2, then I need this many points and so on. So what's min cost t? Well, we're definitely spending 1. And then whatever is the smallest possible amount of points to use for t minus d1, t minus d2 for one of the d's, that's what we're going to use. Make sense? So let's kind of trace it. So what's min cost 0? Min cost 0 is just 0 because 0 points, right? So what's min cost 1? Anyone? Yeah, white. Oh yeah, so one it's cents, right? So economic troubles. Because you can use 1 cent, exactly. What's min cost 2? Yeah, 2. Yeah, exactly. So 2 because 2 1 cent points. So min cost 3. Would be 3. And then min cost 4 is 1, sorry. Because you can use a 4 cent coin. And min cost 5 is 1. And min cost 6 is 2. So at this point, we can start thinking about it in terms of the minimum there, right? So how would that work? So this would be 1 plus min cost 5, because we could use a 1 cent coin, or min cost 2, or min cost 1. Right? So this is saying I definitely am going to use 1 coin, and then what makes sense the most to me? So this wouldn't make sense, because if I use a 1 cent coin, if I use a 4 cent coin, then I'll need to use 2 more, right? So that's not a good option. So this corresponds to using 4 cents. This corresponds to using 1 cent over here, and this corresponds to using 5 cents over there. Right? Does that make sense? So what's min cost 7? Well, first of all, that is why does it think it's 2? It's really 3. It's really 3, right? And that's because it's 1 plus min cost 6 if you use 1 cent, min cost 3 if you use 4 cents, min cost 2 if you use 5 cents. Right? And so on. So I kind of abbreviated a little bit because I needed, so I could, if I wanted to, and you will in the lab, if you want to, you can say that the min cost for negative is just infinity, just so that it never makes sense to like, you just call min cost on a negative number, just get infinity, so that you know that you're definitely not doing that. Okay. That's one way, or you can do an if. Because otherwise, like, I haven't even tried to do the 10 cents, and it's either an if statement, or you just consider negative to always cost infinity. Does that make sense? So are we good with that? Questions? Yeah.
Like I got to 1, 2, 5, and 2, 3, 6 again, because like, I don't understand how we.
So I have my denominations and they start with 6. Right, so I'm saying either I use a one cent coin, in which case the total number of coins is going to be 1 plus min cost 5. Or I use a 4-cent coin, in which case 1 4-cent coin and then whatever it costs to make up 2 cents. Or I use a 5-cent coin and then whatever I need to make up 1 cent. Okay, so this is this. Okay. All right, are we good with this? Okay. So let's write it up. So I'll call it min cost. It's called opt and sometimes people just say opt instead of min cost in the handout. So it's going to get t and it's going to get denominations. And I'm going to say if t is smaller than 0, I'll just return infinity. So this is one way to return infinity. And I'll say if t is equal to 0, then I need 0 coins to make up the amount 0. And then I'll say if t is in any one of the denominations, the answer is 1. And then, so this is valid, but I haven't told you how to do this. So we'll do a for loop. So now what I need to do is I need to basically try every possible thing and see how that works, right? So I'm going to say, okay, so current min is infinity, and then I'll try every possible denomination. And I'll say, okay, so the current minimum is the smaller of the old current minimum or 1 plus min cost t minus d denominations. And then I'm done returning current min. Okay, so this is just like the Python expression of this. Right, so I'm just trying every possible thing. The only thing is it would be annoying to have to say, oh, like if t is greater than some denomination, then just ignore that. So instead, I just say, if you end up with a negative amount, just say that that's infinity coins to make up so that you don't think it's possible because you want the exact amount. Make sense? Okay, so that's min cost. Let's try it. So that's like that. Okay, and the answer is indeed 2. Because 2 4-cent coins. Make sense? All right, questions about Any of that? Okay, so the last thing that I want to do for this topic today is to introduce the last question from today's lab. Is there anything interesting on Discord? Slides. Okay. Is it still worth what 1%? No, it was never worth 1%. I think it's like 3% for the best 8 of 12 or something, right? So okay. So I want to go to the lab. So I'm not kidding about question 1. So I know that not everyone's finished. If you are, then great. If you have stuff to do from previous labs, you can do that. But yeah, like got to do it, got to practice C. So this is a question from the 2024 exam. And the question is like this. So you're given a dictionary of words. So for example, apple and pen. So by dictionary, we just mean like a list of words, right? It's not a Python dictionary. It's just like a list of words. And you're giving a string like something like that, right? So like apple, pen, pull, okay? So the question is, can you segment this thing? Wait, did I misspell it? Yeah, so there should be an A here, sorry. So if there were an A here, I'll fix it. Then it could be segmented into like apple, pen, apple or something. So on the other hand, if you're given something like cats and dog, but just the 1D, that cannot be segmented into those words because like you cannot reuse the D or whatever. Like it could be that there is a letter that doesn't fit at all. Make sense? Does the task make sense? Does the task not make sense? Okay. So you can solve it with kind of the same technique. So here's the technique that I'm proposing here. So let me take this guy. So, and then let me get my dictionary. So here's how I can answer the question of can you segment? Yeah, it's kind of the same approach as with the coins, right? So with the coins, you can say, well, like I got to use one of the coins, and then I'll see what else happens. Here as well, you say, well, like I got to start with one of the words, and then I'll see what happens, right? So I can say, what is it? It's like can segment and dog, or can segment doesn't actually start with dog. So so just so this is like can segment and dog with all of those guys because I was able to take out cats, right? Or can segment so or so here like there is no nothing ever really starts with dog or sand or an and. So that means that that's not going to work. Or you could say can segment sand dog like this. With those guys. Right? Because those are the only possible beginnings there.
First of all, there, does that only have one leaf?
One, yeah, sorry. Yeah, unknown, yeah. All right. So I just check, like can I use cats? Can I use dog? Can I use sand? Can I use and? Can I use cat as the first word? And then I say, well, like if I use cats as the first word, then I just need to know whether I can segment this guy. If I use cat as the first word, then I need to know whether I can segment this guy. Okay. Does that make sense? So one possible plan is try every possible word, cut out the first word, and call this. Obviously, if no possible first word works, then you can return false straight away. Right? So that's pretty easy. So you'll do that in the lab. Okay, questions about this? All right. So we're gonna post like a little bit of practice here. Like I think like if you look at this one, especially like if this is like, the fourth dynamic programming problem that you've ever seen, this looks like how would you ever come up with it? And the answer is like sometimes it's just difficult, but after you've seen a couple of examples, I think it's gonna get easier and easier. Yeah.
Dynamic programming, like quite literally just breaking it up into smaller problems.
So breaking it up into smaller problems and then combining the solutions somehow. Yeah. All right. Okay. Questions about any of this? All right. Okay, I have 9 more minutes, which I'm sorry to say I want to use. So we're starting a new topic. And that's going to be graphs. But it's going to be at first at least it's going to be pretty light. So it's pretty light, 8 minutes. Okay. So here's what a graph is. A graph is basically a set of nodes and a set of edges that connect them. So the nodes are the green things, and then the edges are the sticks that connect the green things. It's a picture. It's a picture that can represent different things. But what is a graph? Well, it's this kind of picture with edges that connect nodes. So in kind of set theory notation, you could say that the graph is a tuple with a set of vertices or nodes. So you can say vertex or you can say node, and a set of edges. And then you have the vertices and you have the edges, and each edge is itself a tuple with 2 nodes. Okay, so that's your basic graph. So far, it shouldn't make sense. So where it should start making sense is if you start thinking about examples of what those graphs could represent. So for example, vertices can represent cities, and then edges can represent direct flights between the cities, right? So you could imagine that each of the vertices is a city, and then between city V3 and V5, there is a direct flight, but between city V1 and city V5, there isn't a direct flight, so that's why there is no edge here. Okay, so in this case, this is like a picture of where there is a direct flight. Here, we're assuming that it's bidirectional, and where there isn't a direct flight. Does that make so? How many people have seen this kind of picture before? So I think not everyone, but like almost everyone. But that's good. Does it make sense now? Does it not make sense to everyone with the flights example? Okay. So all right. So here's a more abstract thing. So you can think about vertices as classes that are scheduled. And you can think about edges as there being an edge if the schedules for two classes overlap. And there's no edge if the schedules for the two classes do not overlap, right? So here, if this is the example, what does it mean that there is no, like in practice, what does it mean that there is no edge between V1 and V5? It means that you can, yeah, go ahead.
Happen at different times.
Yeah, happen at different times. So you can enroll in both of them without a scheduling conflict, right? So you can think about this graph as saying, well, like I want to find a schedule that has as many nodes as possible that are not connected. And that would represent a schedule that's a schedule with no conflicts. Yeah. So that's like the beauty of abstraction, right? So you can think about nodes as being cities and edges as being there is a direct flight between the two cities. And then you can also think as of this same picture representing something completely different. So nodes represent classes, and then edges represent overlap between the schedules for those classes. Okay. Yeah.
And then like
I mean, so you can think about it like that, but the way I was thinking about it is a node is just a class. And then if two classes have conflicting schedules, you draw an edge between them. If not, then not. Okay. Yeah. Yes. Okay. All right. So something even more abstract. So vertices are maybe like objects in memory, in computer memory. And then edges represent whether the two objects refer to each other. So for example, are they nodes in the same linked list or something? And then the idea is that if you can get from one node to another by going next, then you can't just free a node that's referred to by something else. But if you have an object that's not connected to anything, then you can delete it, and there's no danger of the user trying to access it because there's no pointer to it anywhere. Okay. So, all right. So that's examples. So this is just terminology. So you can also have directed graphs. So in this case, the edges have a direction. So just because V1 is connected to V4 doesn't mean that V4 is connected to V1. And you can again think about it in the context of direct flights. So maybe there is a direct flight from city V1 to city V4, but it doesn't go back or something. On the other hand, like here, like between V3 and V4, there is flights both ways, for example. Yeah. Yeah, it is. So a linked list is a specific kind of graph, right? So a linked list is a graph where there is no, well, a linked list could have cycles, but where basically every node is only connected to one next node. Here you have, you know, V1 points to both V3 and V4. So that's kind of the difference. So a linked list is a special case. All right. You could also have weighted graphs. And again, you can think about it as flights, but then like maybe it's like distances or times or costs or something. Okay. And there's other examples as well. I have successfully used up 7 of my 8 minutes. I will see you on Wednesday. Thank you. Bye.